Hey there. Thank you for clicking on this video. In this lesson, we are going to start a sequence on solving exponential equations. This is meant to be an introductory lesson, so if you're coming at this from another class, you might cover this material in a different order, just letting you know. The focus of this lesson is going to be solving exponential equations using like bases. Please give this video a thumbs up if you find it helpful, subscribe for more math content, drop a comment or question below, and please check out the practice set on this material. I'll be sure to link that at the end. Now, since this is our first lesson on exponential equations, it's important that we take a moment to know what we're talking about and how to recognize them. So I define them for my students this way. They are equations where the variable is in the exponent. Okay, so to contrast that with other types of equations where the variable might be the base, or maybe the variable's under a radical, or some other family of equations. So here are some examples of equations that would qualify as exponential equations. So we might have something like this. 3 to the 2x equals 4. Okay, and so that equation has the x up in the exponent, and so that qualifies as an exponential equation. You might see something like this too, say 3 to the 2x equals 6 to the x plus 1. Okay, and in that case, we have x's on both sides in exponent. So that is the type of equation that we're talking about when we are referring to exponential equations. And the challenge posed by these equations, at least at first, until we have all the tools to deal with it, is how do I get the x out of the exponent? We know from our previous solving of equations that I can undo multiplying by dividing. Okay, I can undo adding with subtracting and so forth, but we don't as yet have a tool for undoing how something got stuck in an exponent. You might think, well, exponents are just repeated multiplication, so can't we do some division? Well, like we could if we knew what the variable was and we knew how many times we needed to divide, but we don't. And that's the whole point, is I don't actually know how many times, say, 3 is being used as a factor here because the variable is in the exponent. Now, there are some strategies for solving equations like this. I list them this way, like bases, which is what is covered in this video. And then I kind of break logarithms into two different ways you can use logarithms. One is changing the form over. So I'll have a lesson on that where we kind of talk about recognizing when that's a good strategy to use. And then you could do logarithms by using the log as an operator and taking the log of both sides. Now, I have an asterisk there just as a disclaimer that changing the form is one way of structuring the work, and you can also do that type of equation by taking the log of both sides. So you might have a teacher just kind of show taking the log of both sides, and that's it. And they don't really look at solving those equations by changing the form over, but that is for a future lesson. If you're interested in that, be sure to click on that. Of course, hopefully by the time you're watching this, those videos will exist, but anyway, moving on. Okay, so we want to ground the key idea here, and I'm so big on that in my own classes about not just memorizing a set of steps, but anchoring what the idea is. And so we look at this, what must be the value of x in the equation below? 5 to the x power equals 5 to the 6th power. So you can pause the video, or I'll pause for a moment so you can think about that. And often in my class, somebody will hesitantly just kind of say, well, does x equal 6? Because it seems too obvious. But that is the key idea. And we want the key ideas to be obvious, like that we want them to be the groundwork for how we're going to navigate through these problems. And you could think of it this way. If x were something other than 6, so if you had 5 to the 5th power equals 5 to the 6th power, that would not be true. This is 5 multiplied in 5 times. The other one is 5 multiplied in 6 times, and that's not going to be the same. And you can also go in this direction with it. If you had 5 to the x equals 4 to the 6th, then we don't know what x is, but this we could be sure of. X does not equal 6. And we could actually know more about it than it doesn't equal 6. But like that we're very sure about. X does not equal 6, because in that case, 5 to the 6th certainly would not be equal to 4 to the 6th. Now, what that intro example is doing is it's establishing two things. One is if the bases match, then the exponents would have to be equivalent. That's the only way that the two sides of the equation would be equal. And if the bases do not match, then you most certainly cannot conclude that the exponents are equal. So here's our key idea. If b to the x is equal to b to the y, then x must equal y. And how we want to express this, we could say we de-exponentialize them. I'm pretty sure that's not a word. We could talk about the bases canceling. I get kind of antsy when students say the bases are canceling, not because it's inaccurate, but because a lot of students, when they are picturing that in their head, what they are picturing is division, and it's definitely not division. So if you start showing division in your work, that opens up the door for points deductions, because we're showing something that is actually not true. But the reality is that we can set the exponents equal. Now there's an asterisk there that says b cannot be equal to 0 or 1. Those are like super special numbers. So if you had like 0 to the 3rd power equals 0 to the 4th power, that actually would be true. And the same with like 1 to the 3rd and 1 to the 4th, that actually would be true. And the 0 and 1 are additive and multiplicative identities. They do behave differently. They are my favorite numbers. They are wonderful numbers to turn up, but they're also very special numbers. It's part of why they're my favorite number, that they're very special, which means that they do not behave the way other numbers do, and we want to be cautious when we're using those as our like example numbers. Okay, and so yeah, we just want to make sure that b is not equal to 0 or 1. The chances of you seeing that are minimal. So the rest of this lesson is pretty much like, let's look at some examples. Let's talk about the different things you might see when solving exponential equations using this strategy. The key strategy here is we want to get the same number on both sides of the equal sign. So in this case, we have a 5 and a 5. Generically, b and b. We want these two numbers to match, and we might have to do a little algebraic gymnastics to get them to match. And that's, again, the rest of the lesson is what are the kind of gymnastics you might see. All right, so starting off with something pretty straightforward, with the exception that I've made the exponents a little messier. We have 6 to the stuff equals 6 to some other stuff. And if these two are equal and the bases are equal, then our logical conclusion is that the exponents must also be equal. So 2x minus 1 must equal x plus 1. And what that does is it takes this exponential equation and has transformed it into a linear equation, which we can now solve. So I will go ahead and subtract x from both sides to get x minus 1 equals 1, and then we'll add 1 to both sides, and we get x is equal to 2. And if you wanted to, you could plug that back in and check. Okay, so that is a check. So 6 to the 2 times 2 minus 1 equals 6 to the 2 plus 1. 2 times 2 is 4. 2 plus 1 is 3, and 4 minus 1 is 3. And we can see that those would be equal. Looking at at the next one. So the next one does not have bases that match, and I'm going to be really like overly detailed in how I start doing these. Maybe not on this one so much, but as we go through the next couple slides, because of things that my students had trouble seeing. I just recently taught this in my own classroom. So for a while, my videos were ahead of what I was doing in class. And now, because I've had so much going on and I have not been able to record as much as I wanted to, like my class has moved ahead where my videos are. It's all good though. Okay, so on this one, we look at the larger number here and we ask ourselves, is it possible for me to take the larger of the two bases here and write it as a power of the smaller one? So is it possible to write 27 as a power of 3? That will be different for everybody to answer, like how easily you can answer that. And what I model for my students is this is like your scratch or calculator work. I don't actually need to see this. You might not even need to do this, but you might need to say, all right, well, let's like check it out. So 3 to the first power is 3, 3 squared is 9, 3 cubed is 27, and as I would say, like ding, 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 we have a winner. And so what we do is we take out the 27 and we replace that with 3 to the third power. So you're literally removing the 27 and you are replacing the 27 with an equivalent expression, which is 3 to the third power. And now we have written both sides as a power of the same base, which means that the exponents must be equal. Therefore, 2x is equal to 3. Divide both sides by 2. And I tell my students, leave that as 3 halves. If you want to change that to a decimal, make it 1.5, go for it. But unless the directions ask for it, I'm stopping right there. All right, so let's go take a peek at some other variations on this. Okay, I'm gonna have to re-record this slide because I accidentally referred to myself in the third person. So anyway, moving on, or moving back as the case may be, this problem here, there's two things that are being incorporated in this. One is that we are putting the larger number on the left. And the reason I do that is because I have noticed that many of my students really get hung up on left and right. And in algebra, left and right side of an equation is not a huge deal because A equals B is the same statement as B equals A. It's called the symmetric property of equality. And so when you're talking about an equation, like there's really nothing key about like what's sitting on the left side and what's sitting on the right side, because if you wanted to, you could just switch the order. But what we don't want to do is fall into this habit of thinking, I always work with the number on the right. What we're doing here is we're working with the larger of the two numbers to see if it is possible to write that number or base as a power of the smaller base. Now, the other thing is the exponent here. Now, the x minus 3 is the existing exponent, and the 36 is being raised to that power. So 36, or however we might write the 36. So I use this analogy in class. I say, we're going to call this the super cool exponent club. They are the existing club, and they are not a friendly club, okay? They are the snobby club that doesn't like to accept new members, okay? Membership is closed on the super cool exponent club, okay? So just kind of keep that in mind. So let's take a look at the 36. And you can do this as scratch work, you can do this on the calculator, or you might not need to do anything at all. But we take a look at 6 to the first power, we look at 6 squared, and we're like, oh, we got a winner there, okay? I am going to take out the 36, okay? 36 is coming out of the problem, and I'm replacing the 36 with a 6 squared. So I'm going to pause here for a moment to let you look at that closely. Okay, all right. because we just don't want to rush through this. So the 36 is coming out and I've replaced it with a 6 squared. Now here's where the super cool exponent club is coming into play. They are exclusive. They are not accepting new members. But now that I've rewritten the 36, what I have here is a new member. Okay, we have a new contender for the super cool exponent club. This too is trying to break into the club. And this club is not having it. And what they do is they are going to put up their super cool exponent walls here, and they are going to shut out the newcomer. One year, I apparently got so animated in my description of this illustration that a student said, "Who hurt you?" Which, like, isn't anybody? I was just all into telling the story. Anyway, so the point of that is we need to preserve the order of operations and what is being raised to what power. And so it's the 6 squared that is being raised to the power of x minus 3. And the way that I illustrate it or talk about it is the super cool exponent club putting up their exponent walls. And by putting the parentheses in there, we're able to preserve the correct order of operations. And that'll be equal to 6 to the 3x. Once I get those as powers of the same base, so now we have the 6 on both sides, now I can set the two exponents equal, and you are welcome to multiply through. I usually don't when I am first teaching this because I want to be really clear about what the steps are. I am setting the exponents equal to each other. We are not dividing. Okay, I have had students do this and they'll write it out as division, and that I have to take off points for that because that is not what is happening. We are not dividing both sides by 6 there, okay? Because I don't know how many 6s I actually have there because I do not know the value of x. So that is not what is happening. And for my students, if they show me something like that, I will take off points. Okay, so that's why I kind of back away from the 6s cancel, because I think a lot of students are picturing that in their head, and that is absolutely a no-go. That's not the operation. Okay, what we are doing is we are setting the exponents equal. Now from here, we have our linear equation. So I'll go ahead and distribute my 2, and I'm going to subtract 2x from both sides, and I get -6 is equal to x. Yay. Ta-da. Next problem. So the next one gives us a different twist on it. We have 4 to the 2x minus 3, and that is equal to 32. So going along with what we've been doing is we are going to take the 32 and explore and see, is there a way to write 32 as a power of 4? You can say, I'm going to take the smaller number and keep raising it to a power to see if I can get 32. So here we go. We do 4 to the first power is 4. That's too low. 4 squared is 16. 4 to the third is 64. And you can see that we have a problem. So I jumped from 16 up to 64, and I jumped over the 32. So what that means is I actually can't do that. So this gets a little bit more complicated where I can't write one side as a power of the other. So the strategy here is to look for a number smaller than the smaller base. So I need a number smaller than 4 that I could rewrite both the 4 and the 32. So I'll often ask my students, what do you think that number might be? And somebody will typically say, well, I think it might be a 2. So we'll explore with the 2. 2 to the first power is 2. 2 squared is 4. And we got that one. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32, and I can see that I've got both of those. So what we're going to do here is we're actually going to rewrite both sides. I am physically taking out the 4. The 4 is coming out, and the 4 is being replaced with 2 squared. Super cool exponent club. Okay, we have that existing exponent, the 2x minus 3, and they are not the good cool kids that make other people cool. They're the bad cool kids that just shut other people out. And we are not accepting a new exponent into our exclusive club. Point of that illustration is to remember to preserve your order of operations there. On the right-hand side, we're going to take out the 32 and replace the 32 with 2 to the 5th. Once you have the same number on both sides, now you are free to set the exponents equal to each other. So 2 times 2x minus 3 is equal to 5. And we can go ahead and distribute that 2 through. You are more than welcome to distribute that as you are writing it down. Okay, you do not need to write that as a separate step unless somebody is requiring you to do that. All right, let's add 6 to both sides and divide both sides by 4. And we get 11/4, and again, I'm not going to mess with that. If you need to see what I did, if you thought we just kind of blew through that a little bit fast, I added 6 to both sides, and right in here, I divided both sides by 4. I'm just not showing that process. There we go. All right. So in summary, try writing the larger base as a power of the smaller base. Okay, that's like the first thing we want to try. If this fails, try writing both bases as a power of some smaller number. We just looked at that where we had to take the 4 and the 32 and kind of go to a smaller number. The good news is this, the numbers will not get super, super big. Exponentials, if you recall from graphing them, which was a previous lesson, exponentials grow really, really fast. So once they start growing, they become very, very, well, they explode. Okay, it's explosive growth. And so unless you want to be doing a homework assignment or something that deals with numbers in the tens of thousands, we are keeping them fairly small. And then the second bullet point I have there is preserve order of operations by grouping those exponents. That's our super cool exponent club. Okay, the super cool exponent club. And they are grouping in order to make sure that we're getting the correct order of operations on that. Okay, please do not forget to like this video if you found it helpful. It only takes a moment to hit that thumbs up. Subscribe to the channel for more math help. Ask me a question or provide some feedback in the comments, and check out the practice set linked below. There are some twists and turns on that practice set that you don't want to miss if you really want to become fluent in this strategy for solving exponential equations. And I hope I see you in a future video.